Hi everyone, welcome back to the channel. So there's a paper that's been attracting quite a lot of attention. It's this one, it's called Traversable Wormhole Dynamics on a Quantum Processor. People have been getting very excited because they've been thinking that this is an actual wormhole that's inside a quantum computer. And interesting headline from New York Times saying physicists create the smallest, crummiest wormhole you can imagine.
Baby wormhole.
Yeah, I'm not sure why they're making fun of their wormholes. I'm not sure if the New York Times can do much better. This has actually been quite a controversial paper, in fact, and so there's been a little bit of backlash from people also in the community. So, for example, on Peter Woit's blog, Not Even Wrong. So he's been saying that this is really kind of a publicity stunt, and in fact, he's even calling it nonsense. So what we're going to do today is to kind of dive into this paper and let's see whether this lives up to the hype. So as we know from general relativity, basically, space and time are inextricably linked, and in fact, gravity can be understood as creating some kind of curvature in space. So, this is why we can see interesting effects such as gravitational waves. So when two massive black holes are circling each other, then this is causing ripples in space-time, and then the waves kind of travel out. A fascinating construct which Einstein himself realized quite early on is that the solutions of general relativity actually allow for possibilities of things like so-called wormholes. So wormholes are basically regions of extremely sort of curved space-time where instead of the universe actually just deforming around some kind of gravitational area, it can actually even connect to distant parts of it. And so this invites the possibility that you might be able to travel vast distances by maybe going into a wormhole. A little bit like, in Interstellar when the guy goes into the black
Time
hole.
travel, yeah.
Yeah, exactly, yes. These wormholes are also called Einstein-Rosen bridges. And if you're wondering, hey, that Rosen guy, isn't that guy also in the EPR, right?
Yeah.
So it's actually the same guy. In fact, they published the paper relating to EPR, the famous EPR paper, which is talking about or questioning quantum mechanics, and Einstein-Rosen bridges, as in wormholes, actually in the same year even. So these guys had a pretty good year that year, right? It turns out that actually, if you look classically, you cannot really have a traversable wormhole. So this idea that you can dive into a wormhole, travel in a spaceship, and go out, exit somewhere, classically is apparently impossible because it violates this so-called null energy condition, right? And this is basically, I think, a generalized statement that saying that basically energy is always a kind of a positive quantity, right? In a general relativistic way, this matter energy momentum tensor T, if you look at any kind of arbitrary light vector, should be always positive. So classically speaking, actually wormholes are not really traversable. But recently people have been trying to look at various loopholes through that kind of argument. And there was an interesting paper about 5 years ago now. Actually, one of the authors on this paper is also the author of the recent Nature paper, where they state that actually maybe if you include quantum mechanics, you can actually get around this. But the idea is something like, well, just using classical physics, these wormholes tend to collapse on itself. But then if you have a quantum mechanical particle, then this wormhole can somehow be stabilized. In fact, this connection between this entanglement and wormholes goes even deeper than this, because actually there's an actual conjecture which was introduced by Juan Maldacena, he's a famous particle physics guy, Leonard Susskind, also a super famous particle physics guy. These guys proposed back in 2013 that in fact there might be a kind of a duality connection between this Einstein-Rosen bridge and actually EPR pairs. So not only are the names similar, in fact, there might actually be a mathematical connection between these two things. They outline in this paper is that there are a lot of similarities between these two things. So as we know from quantum mechanics, entanglement doesn't allow for superluminal communication. In fact, we did a video about this a while ago, didn't we?
Yeah.
Same is the case for Einstein-Rosen bridges. Another kind of similarity between wormholes and entangled particles is that just like how entangled particles, they cannot be created by LOCC, and LOCC means local operations and classical communications. In other words, basically, if you want to create entanglement, you've got to bring these things together at some point and then interact them, take them apart, and then you can create entanglement. So the situation, as they say down here, they say for Einstein-Rosen bridges appears to be very similar. So given two distant black holes with no Einstein-Rosen bridge, there does not seem to be any way to create a bridge between them without pre-existing bridges. So they kind of introduced this idea as the catchy name of ER equals EPR because of the two famous papers.
So does that mean that entanglement particles are also connected by these bridges or connections?
I think it's more of a duality connection. It's a bit like how, particular models, mathematical models, can be kind of related to each other through a transformation. Called, I think, in general, this sort of holographic principle that can have like a 2D kind of model, in this case, this 2D hologram, and it actually kind of contains all the information about like the 3D model, right? So you shine light through this 2D sheet, and then you can actually recover the full 3D. Yes, exactly, yeah. So in a similar way to that, you can actually relate these two things. It's famous AD-CFT correspondence, this anti-de Sitter conformal theory, field theory correspondence is kind of an example of this holographic principle. So anyway, so there's this kind of connection between these. So that was a crash course in all the kind of background that you need to kind of know for this paper. So now let's actually dive into this actual paper. So I want to give you first a kind of very quick mental picture of basically what we're actually doing in this paper. Okay, so this is my beautiful diagram that I just drew. So basically the idea is, so you have such a wormhole, and then you bring in an entangled particle near one of the wormholes, or entrances to the wormhole. Okay, and then you put one of the particles inside one of the entrances at time t equals minus t0. Because of this null energy condition, just sticking it in there and then, letting it come out apparently will not actually work in terms of traversing the wormhole. So you need to do something extra. And the thing that they do extra is to kind of create some interaction between two regions of space-time at the entrance and the exit. Okay. And so they kind of interact them in some way. And this creates apparently some kind of shock wave which can kind of get around this null energy condition. I don't completely understand it, but maybe it's something like, it temporarily, violates this energy condition at some point so that it allows to traverse this wormhole. So, okay, let's just take it for granted that you need to include this kind of ingredient. Okay, so after that, the other half of the qubit comes out of the exit of the wormhole, and basically then you take it away from the other side. Now, basically what you want to have here at the end of this is that basically the two particles are still entangled, and basically the particle has safely gone through this whole wormhole such that at the end the two qubits are kind of preserved in their original form. So they're still entangled in their form.
At the two sides of the space-time.
Yeah, that's right. Yes, exactly, far apart. Okay, so that's the kind of thing that we want to do, or they want to do, in this particular paper, right? Because we don't have, regions of space-time and quantum gravity and wormholes and things like that. What we need to do is to map this to an equivalent system that has this kind of duality connection according to this sort of holographic principle, right? So basically, they map it to a particular model of Majorana fermions. In fact, we did another video on Majorana fermions, so if you want to check that out, please have a look. Majorana fermions are basically something like sort of half a fermion, right? So what you do is you have a fermion, and then if you take the real and imaginary parts of the fermion, then this is maybe what you call a Majorana fermion, and so you can consider them to be sort of like a subparticle of a fermion, where if you get two of these Majoranas, put them together, it makes a full fermion, right? So you get a bunch of these Majoranas, which are like half a fermion. So in this case, I've got six Majorana fermions, so that means sort of three actual fermions. And then they interact in some kind of way. And apparently this kind of model is like a jewel to various sort of quantum gravity models, and they're sort of equivalent according to this holographic mapping. So then basically what you do in terms of the actual Majorana model is something like this. So you get two of those Majorana models. There's one on the left and one on the right. Each of those correspond to this sort of patch of space-time on the left and the right. Okay, and you start them in some common sort of entangled state. Okay, so this Majorana model has some set of energy eigenstates, and then you create this sort of entangled state which has this form. It's called a thermofield double. Kind of jargon, but basically it's an entangled state between these two Majorana models, but in the gravity picture, this is actually what corresponds to your wormhole. Okay. Now, what you then proceed to do is you bring in your entangled qubit, okay, to the left-hand side patch of space. Okay, so that's, okay, you have your Majorana system on the left there. Then you perform a swap operation. This basically puts one of the qubits onto basically the Majorana system. Okay, and then you interact the dynamics for some amount of time. Then you have to do this analog of this sort of interaction step. Okay, and the way that they do that is, even though the thing is already entangled to start with, they kind of re-entangle it using some interaction between all the pairs of Majoranas. So the dashed lines, or some kind of interactions between Majoranas, between the left and right patches. Okay, and then they just evolve the system forward again. And if everything goes well, then now the qubit, what used to be like the other half of the qubit that was entangled, the red things here, should be on the right-hand side now. And now we're going to get it out of that patch by using another swap operation, which, again, if it all goes well, then ideally we end up with two entangled pairs that are sort of on either side of this system. Okay.
The Majoranas, are they really physical particles? Have they been actually discovered? Or?
So I think what they would do in the quantum computer case is that you would, again, map that into like a spin system again, right? So you take the Majoranas, you turn that into some kind of spin model. So that, these left and right hand patches are in the end some kind of qubits and spins again. In fact, that's exactly what we did in our paper. We performed a Majorana teleportation on a qubit system. So basically what we did was to map the system onto qubits and then perform the teleportation, again, also on a quantum computer. So this is a quantum circuit. Well, it's written in this sort of different orientation because I think particle physicists tend to draw space-time diagrams where time is vertical and the space is horizontal. This is
from, I think, below to...
Yes, exactly. Yes. So time proceeds upwards in this diagram. And then the initial states are horizontal here. So what you see here, the P and the Q, that's the initial entangled state that you have that you want to, push to the other side. This TFD is that thermofield double state. So that's that entangled state that the two patches and eventually, corresponds to the wormhole. Then the U's here are just a natural evolution of the patches of space-time. The swap is basically putting the qubits inside, actually. And then the V there, the e to the I mu V, is that kind of collision that you do in order to, do this, evade this null energy condition. Okay, so that's basically the procedure that they do. So the first note here, so my first comment is that actually this is quite different to regular teleportation, right? Yeah, because in regular this is quantum teleportation as like what we are used to doing. So in quantum teleportation, actually, we start with an arbitrary state, and then you have some entangled pair. You do some kind of measurement. A form of the state ends up on the other side, and then you do some correction, and then that's teleportation. What we have here is really quite different because we're not sending a single qubit. In fact, we're sort of more like we're sending half of an entangled pair, and we're just sort of transporting it from one side to the other, right? So this is actually not really what we would call teleportation, and even though in the introduction of this paper and various other places, people are saying, this wormhole is kind of corresponds to quantum teleportation. Actually, at least in this one, it looks quite different. So I would kind of not really call this quantum teleportation. I would call this sort of a state transfer. But anyway, that's maybe a small point that maybe it doesn't really matter in terms of what they're trying to show in the dynamics. Okay, so how do they show that they've been successful in the teleportation process or the wormhole traversal process? So what they look at is this quantity called the mutual information, and it's defined like this. Mutual information is I here, and the S is entropy of the system. Yeah, and P and T are the two particles of the entangled pair. Yeah. So if you actually look in their previous paper, which is this one, which has only come out just last year, they actually kind of give quite a concrete scheme for the actual Nature paper that they're doing here with many more details. The key point in this paper is that basically they tell you the significance of this mutual information, which is that actually you get this maximal mutual information when the state is actually a bell pair. Okay, so this I here becomes 2 log 2 when the state is one of these states here that I've shown.
So this is the maximum value.
Yeah, maximally entangled states. And these are the maximal values basically because in an entangled pair, if you trace out one of the qubits, then you'll get a completely mixed state. And then so the positive terms, the S of R and the S of T, those will be like positive. And then for a pure state, S of the common state is 0. So basically, this is what they're actually measuring. It's sort of more like, you can just about say that this I is some kind of just about a measure of entanglement, if you like. So essentially what's going on here is that in an ideal, this teleportation scheme, if you still have the entanglement at the end, then the I mutual information will be large. And you'll have that situation basically if you have a state that's like this. So the wormhole, all that stuff there in the wormhole is completely disentangled to the qubits that you just put in it. And if you have a maximally entangled state, then this I will be large. So that's basically their main quantifying metric for the success of the teleportation. Right?
So in the paper, they claim that they achieve maximum value.
Well, let's have a look.
Yeah.
So they say here that the peak in I is an of quantum teleportation. So, ideally you would say that, okay, you kind of want I to be its maximum value of log 2 log 2. Yeah. But actually in this paper, they already say that actually not really 2 log 2. just a peak is already an indication of quantum teleportation. Okay, and so here is some of the results. So just to understand this graph, so let's first just look at the black and purple curves. Okay, and basically what you're seeing here is the vertical axis is mutual information. So this is more or less like, okay, so how entangled are the particles at the end? Yeah. And then the horizontal axis is, so they have two slightly different schemes of when the initial particle comes out at T0, and then the final particle comes out at T1, and then if they're sort of the same value, they call this a symmetric injection. Okay, so so if you put it in at -5 seconds, comes out at +5, that's sort of the symmetric way of doing it. The fixed injection time means that you just say, okay, I'm going to fix my time that I'm putting in the first particle on the left wormhole, say, at -2.8, and then I'm going to vary the time that the second particle comes out. Okay, so there's two slightly different schemes, but more or less a similar kind of story. Okay, so the black and the purple curves differ by the sign of this mu. And what is mu? It's basically this the interaction coefficient of, remember when in the middle you kind of interact the two wormhole exits and entrances? So it's some kind of interaction coefficient of that process where you interact the two patches of space-time. Right? Okay. So depending on if that's positive or negative, basically they see two different types of curves, and they say that this is like a signature that you need this interaction coefficient to be negative in order to remember you did this to evade this null energy condition thing, and then what they say is that only the negative version will do. In the positive version, this teleportation should not be actually successful. And they kind of say that is, basically what they see. So you can see that the black one, it's got some kind of peak, right? And then it kind of wobbles after that. The purple one is somewhat small for the whole time. Okay. So basically one's got a peak, one doesn't have a peak. And so they say, so teleportation. Right? Well, a couple of points here is that, okay, well, you were going on about what's the maximum value, right? So 2 log 2 is 1.39. Now, assuming that they use the same units, the peak here is, something like 0.23. Okay, so that's like way smaller than maximal entanglement. So, in fact, what you're getting here is not really a kind of an absolute maximal entanglement, but something much, much, much smaller than that, actually. But they still say that that's evidence that this teleportation has worked. So what are all these faint lines? Well, these are for various other different kind of parameters. So this Majorana model can have a lot of different parameters. And then basically it's saying that, it doesn't matter on what parameters you choose, it generally has the same kind of dependence. So in the right curve, you also see basically, black curve having a bigger peak than the purple one. Okay. Next, what they do is they try to simplify the model somewhat. Okay, so instead of looking at this 10 Majorana fermion model, the blue dots are supposed to be Majoranas, and the connections are some, interactions between them. Okay, and they try to say that, even with a slightly simplified model, the thing still has the same basic physics. Okay, so they look at a much more simpler model with fewer Majoranas and also fewer connections between them, because and the motivation for this is that basically they're eventually going to do this on the quantum computer. These are all classical calculations, by the way. This is nothing that we still haven't done anything on the quantum computer yet. This is just regular classical computation. They find this model using some machine learning approach, which I think is basically just some kind of optimization to find a simpler model that still has the same basic stuff. So that's the gold and the green curves. And then basically what you take from here is that the gold curves still have a peak, right? They have a bigger peak than the green ones and still has the same kind of dynamics as you expect. Okay. Now they they use this particular model, so this equation 3 here. This is the thing that they found in their optimizer or machine learning protocol. And they say, okay, so we're just going to use this model from here onwards because this is simpler and it basically does the same job. And basically they study that model a little bit to see if there's anything that is out of the ordinary. And basically what they see is that it does all the kind of expected things. So certain types of quantities, again, so on the left here, we've got this mutual information difference. That's the difference between this positive and negative mu values. And one is supposed to be bigger than the other, and it is. So this learned one, this simpler model, has basically the same kind of trend as the genuine model with all the different interactions, right? So you can see all the faint gold lines here, they sort of follow the same kind of trend. Okay. The thing on the right here is some other quantity, which is some correlator, and again, the point here is that it has the same kind of trend. So basically, this is just to back up their statement that using this simpler model is fine, and it basically has the same dynamics. Okay, so another thing that they check is this so-called Shapiro time. And basically the idea here is that if you stick in like two particles, one's going left and one's going right, basically because of the green one that's going in the opposite direction, these things will scatter, and then the red one will only emerge at a time which is slightly later than it would have otherwise without the green particle, because it runs into it and then there's some kind of scattering dynamics. Okay, and then so they check that happens, and then yes, it does. And so basically they're still trying to say, yeah, this model is good, it does everything that we expect it to. Okay, so finally we get on to the part where they do it on the quantum computer, right? So they use this Google Sycamore quantum chip, which this is some 50-something odd qubit chip, and I think out of the 50 qubits, they only use 9 qubits. However, it's actually a super deep circuit with 164 controlled Z gates and 295 single qubit gates. So it's actually very, very deep, actually, right? Yeah. So I'm surprised, actually, it works actually in this very, very deep circuit, but apparently it does. First, they do a little bit of a sanity check, again, that on the quantum computer, it's simulating this model correctly. And so what they do in this figure here is a kind of a simplified version of that whole qubit swap kind of thing. This time only really with sort of one side of the patch. And so if you look at the circuit diagram here on the right here, basically what they do is they swap in like half of an entangled pair, they evolve the system and then swap it out, and then check that the entangled pair is still intact. Yeah, and then so they look at the mutual information, and then basically what this is supposed to do is just sort of decay, I think. And the gray ones are some regular classical simulation, and the orange ones are quantum computer calculations, and they agree pretty well. So they say, quantum computer is working fine. So this is actually the only results, at least in the main part of the paper, where you actually do the full circuit, but with the quantum computer. And so what's plotted here is the mutual information difference. So again, that's the difference between like the positive and negative energy interaction things. And then so one is supposed to be bigger than the other. And so basically what you're supposed to see here again is that, all these points should be somewhat above zero. Okay. And then so if one peak is sort of bigger than the other, then they say that, this is consistent with the teleportation. And so the gray ones are, again, the simulation values. The orange ones are just regular measurements. Left and right are just these two schemes of the fixed injection versus symmetric injection times. And similar kind of things. So that's pretty much all the results. What do you guys think? Are you convinced? Is there a wormhole in the quantum computer?
Physical picture is, I think, missing here. They try to model it, but still, what features they are using of a natural black hole and comparing it with the quantum states, which they are using with the Majorana.
Yeah. Well, yeah. So definitely it's some kind of mapping, right, between, so you're not literally you don't literally have a wormhole or any black holes
In
or
the
any
labs,
space-time or anything inside the quantum computer. You take that, which is, because they actually fiddle with the model, so it's going to be some weird theory of quantum gravity even, right? And then they, perform some kind of experiments on this dual model, and then they just say, well, it kind of does the things that you might expect is really what they've seen here.
Just transferring the state through this wormhole.
Yeah.
That they're just claiming, which is thing to be quantum teleportation as per their.
So, in the lab, can you really see Mariana females?
Okay, that point. No, not really. No, nobody's had conclusive evidence of real Majoranas.
Okay.
Well, let me say that I kind of feel, so I have to sort of say, that I kind of feel like, they say that these are all signatures of wormhole, but is it so unique to this system? Like, if you just took just about any model, right, and then you swapped in something and you interacted it, and then you checked that this particle gets transferred to the other side. Okay, or let's think of a simpler example. So you just often, I think people in quantum information, they actually do this very thing where they do some kind of quantum transfer protocol, right? So you stick in a qubit at one end. It's a complicated model, but then it goes through and then it emerges at the other side, right? Okay, so I kind of feel like just about any model would actually do this. And so, is this absolutely a signature of, quantum gravity? Is it really a signature of a wormhole? I just can't help but think that I'm a little bit skeptical that, this is really a unique feature, particularly, if you've got so many free parameters to play with. You're playing with all these, interactions between the model. You're playing with, all the times. You kind of can optimize so many things that, you can just about get anything you want. That's just kind of my feeling. And I don't know.
I'm just thinking, I don't know, maybe I'm going to, but assuming you put an entangled pair in a double well, for instance, and somehow, maybe initially the wells are far apart and things like that, so there's no tunneling, and eventually you bring them closer and see, you now check to see whether
Transfer.
one of the transfer. Will it mimic this exactly? Because that's what I've been thinking. I don't know.
I think it might, yeah. That's an even simpler model, but I guess the difficulty of this one over maybe your example is that, the thing that it has to traverse across, right, is actually a pretty complicated model, right? So it's not like a nice clean system where there's no interactions. This is some highly complex thing, and so it has to sort of get through unscathed through all that, right? So that's what this is. It is more difficult in that sense, but then I think that like we're not seeing like perfect fidelity or anything like that, right? It's like way low. So to some extent, I kind of expect it to happen. And if we're looking at tiny bumps in the data, I don't know. Is it unique? I'm a little bit worried about that point. Let's say.
So this is all about just particle transfer or something like that.
Yeah, it's sort of particle transfer. Yeah.
If you are doing particle transfer, something like the twin paradox, right? You remember? So, you normally check to see whether if this one has aged or, something like that. Can you really
I see.
In that sense for this kind of thing?
I see. So like, ticking clocks.
Ticking clocks.
Yeah.
Exactly.
So, some kind of time dilation.
How has it affected the clock of the particle that went through the wormhole? Is it still the same or is it different?
I guess, you would have to map it back to the quantum gravity model.
Okay.
And then see what that corresponds to in the original model, right? So, what kind of quantum gravity model you end up with, I don't know.
I don't know.
Yeah. tell us in the comments. All right. Well, thanks for watching. Hope that was informative, and see you for the next video. Bye.